Algebra 2 Lesson 6-6, Function Operations. A composite function is the putting together of two or more functions. The output of the first function becomes the input of the second function. And you can add, subtract, multiply, and divide functions based on how you perform these operations for real numbers. One difference, however, is that you must consider the domain of each function. So in other words, if you have f plus g of x, it's the same thing as saying f of x plus g of x. F times g of x is f of x times g of x. F minus g of x is f of x minus g of x. And f divided by g of x is f of x divided by g of x, provided that g of x is not equal to 0. But, however, the thing you must remember, the domain of the sum, difference, product, and quotient functions consists of all the x values that are in the domain of both f and g. Also, the domain of the quotient function does not contain any x value for which g of x will equal 0. So in other words, you have to be able to know what your domain is as well. All right, so adding and subtracting functions. If we let f of x equal 2x squared plus 8 and g of x to equal x minus 3, we're going to find f plus g and f minus g. Okay, of x, obviously. Okay, so f plus g of x. This means we're going to take f of x, 2x squared plus 8, and we're going to add to it the g of x, which is x minus 3. So we have 2x squared. There's no other x's, so 2x squared. There are plus x, and then 8 minus 3 is 5. Now, the domain. We can put in any number for x in either one of these. I can put in any number for x here, and it's not going to change anything. And I can put in any number for x in this function, so it's not going to change anything. So the domain is all real numbers. Okay? So my domain here is all real numbers. So here we have that answer. Now let's do f minus g of x. So we're going to have 2x squared plus 8, and we're going to subtract from that x minus 3. I put them in parentheses because remember when you subtract it to run the negative all the way through. So you end up with 2x squared minus 8, plus 8, minus x plus 3. So when you simplify this, you get 2x squared minus x plus 12. I almost said 11. All right. No, it is 11. I was right the first time. Okay. 8 plus 3 is 11. Okay. Again, my domain is all real numbers because if it was all real numbers of the other one, it does not change here. So my domain is all real numbers. There's no number I can put in for x, which is going to give me an undefined answer, so I can have all the numbers. All right, multiplying and dividing. Let f of x equal x squared minus 1 and g of x equal x plus 1. We're going to find f times g and f divided by g, and what it means. So f times g of x is going to equal x squared minus 1 times x plus 1. We're going to multiply this out, and I'm going to get x to the third plus x squared minus x minus 1. And there are no like terms to combine, so that's what we get. X to the third plus x squared minus x minus 1. Do I have to worry about getting an undefined answer? No, because there's no denominator. So my domain is all real numbers. There we go. There's f times g of x. Now we need to do f divided by g of x. So that's going to become f of x divided by g of x, which is going to be x squared minus 1 over x plus 1. Now, interestingly enough, we need to factor out x squared minus 1. Because if you leave it like this, if you leave it as x squared minus 1 over x plus 1, it's not simplified. This actually factors to x plus 1 times x minus 1 all over x plus 1. These x plus 1s will cancel out, so you end up with x minus 1 as your answer to your division problem. But you have to look at your original problem way back here to figure out your domain. If I look at this, my domain will be all real numbers except x cannot equal -1, since x cannot equal -1 in the original expression. Even though my answer is x minus 1 over 1 and I don't have a denominator, so I shouldn't have to worry about it. Remember, my definition of a function, the domain has to fit, okay? The domain of the sum, difference, product, or quotient functions consists of the x values that are in both the domain of both f and g of x. Now here, the domain here is if x equals -1, I get 0 in the denominator. I can't have a 0 in the denominator, so my domain here is all real numbers except x equals -1. Okay. All right, now, the diagram at the right shows what happens when you apply one function, g of x, after another function, f of x. Notice the domain of f, you get the input of f of x. Okay? The range of f, you get the output of f, which is f of x, the input of g, and the output of g. Okay? This is what you're looking at here, right here. You end up with what's called a composite function. Okay? The output from the first function becomes the input for the second function. And when you combine the two functions, as in the diagram, you form what we call a composition of functions. Okay? The composition of functions says the composition of function g with function f is written g dot f. And notice the dot is empty and is defined as g, and it basically means g of f of x. The domain of g of f consists of the x values in the domain of f, for which f of x is the domain of g of x. To solve a composition of functions, you evaluate the inner function f of x first, and then you apply that answer as the input to the outer function. Function composition is not commutative. Okay? Since f of g of x does not always equal g of f of x. Okay? It's not commutative. It's really important. Okay? Sometimes they work both ways. A lot of times they don't. Okay. Composing functions. There's two ways to compose functions. And I'm showing you both these ways, but you can choose which one you want to. Method 1, we have g of f of x. Maybe write it g of f of x like this. They say take g of x minus 2. So they say, this is not the way I do it, by the way. Okay? I do f of x first, and then I do g of f of x. Okay? So we're finding, whoops, I love how my God disappeared. We're finding g of f of -5. That would help. There we go. Something got lost in my copying and pasting. Okay, so we do g of f of x. Okay, first thing you should do is you're going to find. They say do this. This method 1 is you take f of x, which is x minus 2, and you plug it in there, and then you're going to take g of that. And g says you're going to square it, so you're going to take x minus 2 and square it. Okay? Then they tell you to plug in the -5. So then they say -5 minus 2 is -7, square that is 49. That's not the way I do it. I mess up every time I do it by method 1. I always use method 2. G of f of x to me says take f of -5. So if f of x is x minus 2, then I'm going to take -5 minus 2 and I get -7. Then I'm going to take g of -7, so I'm going to take -7 and square it and get 49. I think this method is cleaner. I don't care which method you use as long as you're good at it. I'm only going to work with method 2, so if you're going to watch examples, you're only going to see me do method 2, because it's the only method I'm really, really good at. I mess up method 1 every time. Okay, so now let's let f of x be x squared and g of x be x minus 3. We're going to find g of f of c. And you might go, what? Now we're going to put in c's in the things. G of f of c means, basically, I'm going to find f of c first, which is going to be f of x was x squared, so now I'm going to place c squared. Okay? Now I'm going to find g of f of x, f of c, which is c squared. Okay? So g of c squared says every time I see an x in my g of x, I'm going to replace it with c squared. So now I have c squared minus 3. Okay? So g of f of c is c squared minus 3. G of f of 1/2. And I'm going to take f of 1/2. Okay? So f of x is x squared, so I'm going to take 1/2 and I'm going to square it. That becomes 1/4. So now I'm going to take g of 1/4. Okay. So now I have g of 1/4. So g is x minus 3. So that's going to become 1/4 minus 3. So that's going to be negative 2 1/4, right? Excuse me, negative 2 3/4. Okay, so this answer is going to be negative 2 3/4, which can be written as negative 11/4, or it can be written as negative 2.75. I don't care. I can write it. They're all three the same thing. Sometimes you'll get an answer like these right here, negative 2 and oops, about the negative 2 3/4, and negative 11/4, and negative 2.75. Sometimes you'll get an expression. It doesn't matter. There's still composition of functions. All right, f of g of negative a. So I'm going to take, now I'm taking g of negative a, and g says to take x minus 3, so it becomes negative a minus 3. So now I'm going to take f of negative a minus 3. And f, we're supposed to square that, so I get negative a minus 3, and I'm going to square that. Okay? So remembering how to square this. Okay? I'm going to square this. If you're not really good at squaring, remember it's negative a minus 3 times negative a minus 3. So that's going to be a squared plus 3a plus 3a plus 6a plus 9. That's the answer for that one. That's the composition of functions. And you might say, what in the world do we use composite functions for? Well, let's take a look at this good example right here. A store is offering a 15% discount on all items. Also, employees get a 20% employee discount. Write a composition of functions. A model taking the 15% discount and then the 20% discount, model taking the 20% discount and then the 15% discount. You might say, well, they're the same. They're not. They may or they may not be the same. Sometimes they are, sometimes they're not. Okay, so I'm going to let d of x equal my store discount. Okay, which would be x minus 0.15x, or it's 0.85x, right? I'm going to let e of x equal my employee discount. Which will be x minus 0.20x, or 0.80x. And x is obviously the cost of whatever the item is. So, let's take a look at this. We want a model taking the 15% discount and then the 20% discount. So we want d of e of x. There we go, d of x. Okay? So that's going to be e of x, which is going to be 0.8. Okay? So we're going to get, and then we're going to multiply that by e of x, which is 0.85x. So you're going to get basically 0.68x. So you're going to pay 68% of the total cost. And let's do the other way. Let's do e of d of x. Okay, so now we're going to do d of x, which is 0.85 on the outside, times 0.80x, which consequently in this particular case, since you're multiplying the same numbers, ends up being the same thing, 0.68x. It doesn't always work that way. Sometimes it's better to take one discount before it is to take another discount. Sometimes they don't let you compound discounts. It's really nice when they do. So obviously, in either case, you're paying 68% of the original. So if you were an employee, it doesn't matter which discount you would take first. If you're just a regular person, you have to take just the store discount. But if you're an employee and you get both discounts, it doesn't matter which one you take first. Obviously, if they only let you take one, you'd obviously take the employee discount over the store discount because it's more. All right, that's functions.